Welcome to Week 10 Supply Chain Design course. Our topic at Week 10 is inventory management. The trade-off, service level versus cost, is one of the most important issues in inventory management. Its resolution strongly depends on the manufacturing, sourcing, distribution, and supply chain strategy. In practice, inventory is classified into either dollar volume using ABC analysis or physical volume using XYZ analysis. Both analyses minimize on-hand inventory by reducing space per unit of item or holding cost per unit of item. Therefore, both classifications are optimized by finding optimum production and order capacity or economic production quantity and economic order quantity. In economic order quantity or EOQ, a PPIC or Production Planning and Inventory Control Manager finds reorder point as a point where he or she needs to order additional material or items to suppliers in order to meet future demand. However, the demand is never been the same at any time, and therefore, the manager needs to formulate inventory model by incorporating stochasticity of demand and measure its department service level. Considering that inventory and transportation need to be synchronized, we will learn the effect of inventory aggregation with regard to transportation and logistic constraints. Finally, we also learn about ATP or available to promise or CTP or capable to promise as a way to satisfy customers by modifying production plan to be capable to promise to customers and therefore be available to deliver product to them. Consider three examples. You can read the examples in the textbook of this course. For Amazon, Amazon.com Incorporation is the world's largest online retailer, founded in 1994. It started as an online bookstore, but has diversified over the last 20 years, selling DVDs, CDs, MP3, software, games, furniture, food, toys, and more. The basic idea is that everybody with access to the internet can buy nearly worldwide a massive range of products at any time and get them delivered wherever they want. Amazon apps makes it possible to buy their products easily, even with smartphones or tablets. Their inventory management for books is based on the number of sales for each book. Best-selling books are stocked in many regional warehouses to enable fast responsiveness for customers in any region. Books with smaller number of sales are stocked in only a few regional warehouses to reduce inventory cost. The slowest moving books are not even held in stock but are obtained directly from the publisher or distributor. Through this strategy, it is possible for Amazon to reduce inventory cost for slow-moving products and to have the best possible service level and reliability for their customers. The second case coming from Volkswagen, founded in Germany in 1937, Volkswagen implemented the GIT-based supply chain strategy in Germany. This means that components and items are delivered to the assembly line when they are needed. In this case, only a small amount of safety stock is held for critical parts. This strategy helps to reduce inventory, transport, labor, and administrative cost. Often, suppliers locate their plants close to the manufacturer to deliver the required components and items at the right moment, and also to reduce their transport cost. This choice is location reduces the risk of delivery delays and supply shortages. Examples of these GIT components are the dashboard with all electronic devices or seats. GIT is normally used for A, B, X, and Y items. For C items, Volkswagen uses a Kanban replenishment system to have them in stock at any time. These items normally have low inventory holding cost. Based on just-in-time strategy or JIT and Kanban replenishment system, Volkswagen is able to minimize inventory cost. The last case study coming from Dell. Founded in US in 1983, Dell runs make-to-order production strategy. The assembly starts and materials are replenished only after a customer order. In such a business model, Dell is able to drastically reduce its inventory. For some components, Dell has 90 inventory turns a year, which means that inventory is only 4 days on hand by average. Such inventory dynamics allow Dell to respond to a wide range of quantities demanded, meet short lead time, handle a large variety of products, build innovative products, and handle supply uncertainty. From the case studies, we get some insights on how to trade off service level and inventory in inventory management. In addition to the trade-off, it is important to classify items based on monetary value and volume in order to minimize logistic cost due to space limitation and slow-moving inventory. Therefore, we learn ABC and XYZ analysis, matching supply and demand, needs a supply chain manager to find economic order and production quality or EOQ and EBQ. Now we go to material classification based on ABC analysis. For ABC analysis, there are three classes of products. Class A, that is high annual dollar volume. Class B, medium annual dollar volume. And Class C, low annual dollar volume. ABC analysis is used to establish policies that focus on the few critical parts and not the many trivial ones. This method implements the Pareto principle, which states that there are few critical and many trivial. Consider a simple example. Imagine that you have 10 Lego blocks. 2 of them are red, 3 green, and 5 blue, like figure in our slides. To perform the ABC analysis, we measure the annual demand for each inventory item times the cost per unit. Assume that one red block costs $1, one green block costs $0.1, and one blue block here is a white block costs $0.01. You can easily calculate the total inventory cost. It is 2.35. From 2 red blocks takes only 20% of the total inventory amount, but they create 85% of the inventory cost. So the total inventory cost is 2 plus 0.3 plus 0.05, meaning 2.35. However, for the middle Lego, the B items cost 0.3. But the highest number of items, that is the white block, cost the least at 0.05, so only 2.2%. These are critical items in the A group. A items have to be managed spatially carefully. First, it has to be managed for the relationships with suppliers of A items, for instance, by developing supplier relationship management. Second, tighter physical inventory control for A item is needed. Third, we need more care in forecasting A items. Now let's go to the current example. We have to classify products X1 to D3 into one of the three categories A, B, or C. We are given annual demand and the cost. To determine which table lumps are in the A, B, or C category, we need to calculate the annual expenditure. While the annual expenditure is calculated by multiplying annual demand with cost per lump or cost per unit. The next step is to arrange the different types of table lumps according to their annual expenditures. Cumulative expenditure is sum of annual expenditure from the highest annual expenditure to the current sequence of annual expenditure. After calculating the cumulative expenditure, we have to compute the percentage of cumulative expenditure. Then we can classify the A, B, and C items. Assuming that classification is 80 and then 80% it is categorized as A, and then 15% categorized into B, and 5% into C. So we can label the different products according to our table on our slides. Right? We can observe that 150, that's y1 plus t2 plus y4 plus x3, the total number of demand is a relationship between cumulative percentage demand and expenditure is shown in the graphic in the slide, where it can be observed that 80% of the expenditure is created by only 20% of demand. This slide shows different methods of item classification, namely X, Y, Z analysis. The analysis classifies items based on physical volume of the items, demand patterns, or delivery time. For example, regarding the physical volume of items, it is possible to classify unwieldy items in group X and small and handy items in groups Y and Z. The principle will be the same as for ABC analysis. Another option for XYZ analysis is to divide inventory into three classes based on different demand patterns. For instance, class X is constant, non-changing demand. Class Y, neither constant nor sporadic demand or fluctuating demand. And class Z, the sporadic or strongly fluctuating demand. Changes in demand make it possible to determine the prediction accuracy of each inventory class. Information on X, Y, and Z analysis provides the opportunity to develop strategies concerning an alternative stocking arrangement. Also to develop strategy for reorder calculation and intervals of inventory control. So we can see in this slide the connection between ABC and XYZ analysis. For instance, here XYZ analysis combined with ABC analysis will define the purchasing method for different inventory classes and helps to determine which parts must be in stock, like demand oriented, when they should be ordered by using JIT or just in time, when it is only viable for them to be ordered on a forecast basis, like upon need. The role of inventory is to strike balance between inventory investment and customer service. The role becomes important to accompany cost reduction since inventory investment represents as much as 50% of the total invested capital. Thus, in supply chain and operation management, minimizing investment without reducing customer service level has two objectives of deciding when and how much to order. There are several functions of inventory that determines where customer order decoupling point or CODP must be placed to decouple a company and the supply chain from fluctuation in demand and hold a stock of goods that will provide a selection of customers. As a result, a CODP placement supply chain is able to increase its flexibility and resiliency by hedging against supply disruptions. Inventory is also useful to be a buffer to a particular production process that is classified as a bottleneck and therefore smooth the production flows. Finally, inventory is a way of a certain company to take advantage of quantity discounts and hedge against inflation, even though sometimes that policy creates a bullwhip effect that destroys the supply chain coordination. There are different types of inventory, depending where it is defined. There are raw material inventory for purchased items prior to production, work in process for semi-finished product, maintenance, repair, and operating or MRO inventory for items which are necessary to keep machinery and processes productive, and finally, finished good inventory for items that are ready to be shipped to final customer. Inventory costs are categorized into variable holding costs. Those are costs for holding inventory. Can be cost for renting a warehouse, hiring workers, and etc. Ordering costs are fixed that include cost of placing an order and receiving goods. These costs are included in the determination of the economic order quantity for inventory items. Examples of ordering costs are cost to prepare a purchase requisition, cost to prepare a purchase order, cost of the labor required to inspect goods when they are received, cost to put away goods once they have been received, cost to process the supplier invoice related to an order, cost to prepare and issue a payment to the supplier. In manufacturing, setup cost is the cost incurred to get equipment ready to process a different batch of goods. Hence, setup cost is regarded as a batch level cost in activity-based costing. Setup cost is considered to be a non-value added cost that should be minimized. Setup costs include the following: cost of changing the tools or dies on the equipment, preparing and moving materials or components to the equipment, testing the initial output to be certain it meets the specification. Finally, stock out cost is the lost income and expense associated with the shortage of inventory. This cost can arise in two ways, which are sales related, when a customer wants to place an order and there is no inventory available to sell to the customer. The company loses the gross margin related to the sale. In addition, the customer may be lost permanently, in which case the company also loses the margins associated with all future sales. Second, internal process related. When a company needs inventory for a production run and the inventory is not available, it must incur costs to acquire the needed inventory on short notice. For example, the firm may need to pay a rush fee or an overnight delivery charges to obtain the inventory. In addition, the production planning staff must scramble to adjust the production plan, advancing some other jobs in the schedule to replace the jobs that cannot be run until the required inventory have been received. According to their functions, inventory is classified into cycle and safety inventory. The goal is that cycle inventory is to achieve economy of scale and safety inventory to hedge against demand uncertainty. Cycle inventory exists because producing or purchasing in large lots or batches. We can exploit economy of scale and order in large lots to reduce fixed cost. With the increase in lot size, however, also comes an increase in carrying cost. Second is safety inventory. Is carried to satisfy demand subject to unpredictable fluctuation in demand and lead time and to reduce product shortages. Safety inventory can help us to improve product availability in the presence of the uncertainty. In the presence of safety inventory, cost of shortage or cost of overage can occur. Calculation of safety inventory is based on predetermined service level. For cycle inventory that are formulated deterministically, there are four models that are used in managing inventory to match supply and demand. They are basic economic order quantity or EOQ, production order quantity or EPQ, quantity discount, and reorder point models. For economic order quantity models, some assumption holds that demand B and lead times T are known and constant. At time T, a company receives inventory in quantity Q instantly and complete. The model disregards quantity discount and therefore immune against demand changes. The inventory costs are setup and holding costs. Because the inventory replenishment is automatic, no order cost. Since the demand is constant, then a chance of stock out is equal to zero and therefore no need to invest in stock out cost. In EOQ model, cycle inventory is just the average of the quantity of inventory replenishment and the holding cost is C equal to Q over 2. Annual order is simply the demand divided by the quantity of inventory replenishment. Therefore, fixed order cost is F as unit order cost times the number of order. Expected time between order is 365 days in a year divided by the number of order per year. In this slide, we have two inventory costs according to economic order quantity as follows. The total cost or total inventory cost TC equal to C times Q star divided by 2. C is the unit inventory cost times Q star. Q star is economic order quantity divided by 2 plus F that is ordering cost times P. P is demand divided by Q star, and therefore Q star divided by 2 times C is inventory holding cost, and F times P over Q star equal to fixed ordering cost. As we can see in our figure, that Q star is achieved whenever the inventory holding cost is equal to fixed ordering cost. That is in this at this point, a point where this equal to this equal to this. Okay, and therefore in order to simplify the calculation, and this stands for inventory holding cost, and this stands for fixed ordering cost. If we trying to eliminate this Q, and then we have to multiply this equation by Q, and this equation by Q, and therefore we have C times Q square divided by 2 equal to F times B. Alright? And therefore Q star equal to F times B times 2 divided by C, and we have Q, or the economic order quantity, equal to 2 FB divided by C, and it is according to this equation. Alright? Let's work with an example in this slide. Demand for Sacred 2 LED TV at Amilos is 3,200 units per quarter. Amilos charges fixed costs of $2,500 per order. Annual holding cost per LED TV is $80. So the question is that to calculate the number of LED TVs that the store manager should order per refill. First, we have to understand all numbers provided by this question. First, annual demand, that is P equal to 32,000 units because it is per quarter, and then we have to multiply by 4 here. It is per quarter because it is per quarter, and therefore we have to multiply by 4 because we would like to calculate annual demand, and therefore we have 12,800 units per year. The ordering cost, that is F, equal to $2,500 is here, $2,500. The holding cost per unit per year is 80. This holding cost per unit per year equal to 80. And then by using economic order quantity formula, the optimum order quantity, or EOQ, equal to, we back to our previous equation, that Q equal to 2 times P, that is the demand, times ordering cost divided by C, right? 2, and then we have the demand 12,800 plus the ordering cost, that is 2,500 divided by the inventory cost per unit per year, that is $80, and then we have 895. And to minimize total cost at Amilos, the store manager orders 895 according to the result above. LED TVs per refill. The cycle inventory is the average resulting inventory and is calculated as follows. The cycle inventory is Q over 2. Here we have Q equal to 895, and then divided by 2 equal to 448. For order size at 895, and then we have the number order per year equal to how much? 12,800 divided by 895, because 12 1,800 is the total demand in a year divided by the number of economic order quantity, meaning that how many times in a year the company will order. And then we have 14.3. It can be 15 times or 15 orders a year. And then expected time between orders, 365 days divided by 14.3 equal to 25.5 days. So uh, every 25.5 days, that company will make new order. The total cost is therefore equal to 80, that is the holding cost, times 895 over 2, that is the average inventory, plus 2500, that is holding cost, times the number of order, that is 12,800 divided by 895, 14.3. All right, and then we have 71,554, and the total cost is 71,554 for 14.3 orders with 895 LED TVs each order. All right, that's the total cost. In this slide, we will learn another type of economic order quantity, that is economic model with quantity discount. In our slide, inventory cost is defined as function of unit purchase price of an item, inventory holding cost, and order cost. We see that discount rate R reduces the total inventory cost. Here, the R here reduces the total inventory cost. And then the question assumes that holding cost is a function of capital commitment or interest rate and discount rate. Here we have interest rate and discount rate. Since discount rate is not accepted for EOQ, then we have only interest rate, and therefore we have the following equation. And according to the previous economic order quantity model, that in order to find Q star, and therefore we exclude the purchase cost from calculation. And then in order to find at what amount of quantity we need to order with regard to some amount or some discounts that are available. For each discount, we need to calculate Q star. If Q star does not qualify for a discount, we choose the smallest possible order size to get discount, and then we compute the total cost for each Q star or adjusted value from step 2, and then we can select the Q star that gives the lowest total cost. And therefore, we work on the next example to get more understanding about how to operate this discount into EOQ model. Carlo Incorporation operates a chocolate shop in New York. The chocolate is ordered from a supplier in Switzerland. Normally, cost for 1 unit of chocolate is $5, but a quantity discount is provided by the manufacturer. For order up to 999, no discount, and therefore the price is full at $5. But if the order increase from 1,000 to 1,999, then the chocolate supplier will give 4% discount, and therefore the price will be $4.8 per unit of chocolate. And if Carlo Incorporation would like to again increase the amount of order from 2,000 to 10,000, then 10% discount can be given. And therefore the price will decrease by 10% from $5 to $4.5. And the task is that to find at what quantity this company, Carlo Incorporation, must order to its supplier in Switzerland. Okay, we know the interest rate is 20% per year. Okay, let's now try for no discount, meaning that R equal to 0, and we put all information into equation for finding economic order quantity. That is 2, the square root of 2 times demand. The annual demand is 10,000 according to our problem here. The annual demand is 10,000 and the order or setup cost per order is $50. And then we times 50 and divided by 5. 5 is the price without discount, and then times 20%. Right? That is interest rate. And then we have 1,000. Cost, the total cost for ordering without discount, we put our Q star into this equation, into total cost equation. And then we have 51,000 as a total cost, right? So it comes from the price times 1 minus R, no discount, times the annual demand, plus Q star divided by 2 times price 1 minus R is 0, times the interest rate 20% plus this order cost. How many order? 10,000 divided by 1,000 equal to 10 times 50. 50 is the order cost, equal to $51,000. And therefore we now continue to another calculation by assuming that the discount is 4%. And therefore if the discount is 4%, then we have to order at 1,021. We do the same as we calculate economic order quantity without discount. Since 10,021 is between 1,000 and 1,999, and therefore it is valid for cost calculation. And then we have finally 48,980, which is lower than ordering without discount. Okay, now we try to increase by the ordering more than 1,999. Let's say 2,000 for getting 10% discount. But the order quantity for this getting discount 10% is 1,054, which is less than 2,000, and therefore it's not acceptable. But if we insist ourselves, or insist the company, that is the Carlo Incorporation, to order with 10% discount, and let's say we choose 2,000 as order quantity, and then we found 46,150, which is lower than getting 4% discount. And therefore it can be observed that we have the lowest total cost with 2,000 units of chocolate per order. And then we can also determine an expected number of order per year by taking 2,000 as order quantity. That is M equal to 10,000 divided by 2,000 equal to 5. Meaning that every year we order 5 times, and the time between orders is 365 days divided by 5 equal to 73 days. So every 73 days the company will order to the manufacturer to the supplier in Switzerland. Now we go into economic production quantity model, or EPQ model. The EPQ model is fairly similar to the EOQ model, but it is applied to manufacturing. This model is used when inventory builds up over a period of time after an order is placed. Units are produced and sold simultaneously. In EBQ model, we realize the assumption that receipt of inventory is instantaneous and complete. Now we are allowing receipt of inventory for a period of time and introduce three new parameters. First, R, it is daily production rate. D is daily demand. D is the length of the production run in days. I is maximum inventory level. Now we try to derive the economic production quantity model. We can return to our previous formulation for E, economic order quantity. Okay. Let's go to our previous formulation. That's here. The order cost equal to inventory cost. But in our current case, it is order cost should be equal to setup cost because we are talking about production. So we can calculate here. We have order cost here. F B over let's see, FB over Q FB over Q should be equal to setup cost. And then we do the same mechanics. For instance, here by multiplying by Q then we have C Q squared over 2 times 1 minus D divided by R equal to FB. And then if we would like to find Q squared, it is equal to 2 times FB divided by C times 1 minus D over R. Okay, and then Q equal to square root of 2F times B divided by C times 1 minus D over R. What is D? D is the daily demand and R is daily production rate. So what is special about this equation? That demand should be lower and must be lower than the production rate, and therefore the capacity of those particular facilities will be able to meet the demand. Okay, we have also another formulation about maximum inventory allowed, that is Q here, Q times 1 minus B over R. And similar to the formulation for economic production quantity, that P that is the demand and R is the production rate. Okay, and therefore using this two equation, we assume that the capacity of a particular facility is always be able to meet the demand. Now we have an example that Natural Incorporation produces high-quality food processor. It sells 18,000 processors per year and is able to produce 125 machines per day. Natural Incorporation is working on 250 days per year. Annual holding cost per food processors is $18 and setup cost is at $800. We have to calculate economic production quantity for Natural Incorporation and the maximal inventory level. First, we have to calculate the daily demand. We have information about annual demand, that is 18,000 processors. and therefore we have to divide by 250 because the working day in a year is at 250 days. Okay, and therefore we have 72 units per day. And then we put into our equation for economic production quantity, and then we have 1943 as a optimum production capacity and the maximum inventory at 824, and therefore it can be observed that the optimal lot size is 1943 units. At this quantity, minimal setup and holding costs can be achieved, taking into account the actual consumption rate of 72 units a day and a production rate of 125 units a day. Maximal inventory level in the system will be 824 units. Okay, now we go to reorder point. What is that? Reorder point is a point that gives signal to production planning and inventory controller to make an order to suppliers. And the economic order quantity answers the how much question, but reorder point tells when to order. So reorder point is introduced to take into account the so-called lead time between placement and receipt of an order, and therefore reorder point is formulated as the daily demand times the length of lead time. Okay, now we have an example about reorder point. A company experiences an annual demand of 8,500 cheese knives per year, or 250 working days. Lead time for an order is 5 working days. We have to calculate the reorder point and explain its meaning. The daily demand is that 8,500, the annual demand, 8,500, this to here, divided by the working days, 250. And then we have 34 units. And therefore, the reorder point is that simply 34, number of units produced or demanded, times the 5 days. Alright? And we have 170 units. When we reach the inventory at 170 units, we have to place a new order, or otherwise we will have an opportunity of having stock out. In the previous discussion, we focusing on deterministic inventory model, meaning that the demand is always fixed, never changes, and smooth from time to time with the same amount. But here we talk different kind of demand. The demand is stochastic, means it is predictable, but it's not static and not always the same from time to time. In many practical cases, both demand and lead time are fluctuating. We do not know their determined values, but can only estimate them on the probability basis. For such cases, stochastic or probabilistic models are needed. Uncertainty in demand makes it necessary to maintain a certain customer service level or level of product availability to avoid stockouts. Service level is a fraction of demand that is served on time from a product held in inventory. A high level of product availability provides a high level of responsiveness but increases cost because a much inventory is held but rarely used. The basic trade-off when determining the level of product availability is between the cost of inventory to increase product availability and the loss from not serving customers on time. Now we have practical insights before going further into formulation of stochastic inventory control. In practice, different service level estimation are used. For example, in any logistics software, that is software for supply chain simulation, use three service level indicators. The alpha service level measure the probability that all customer orders that arrive within a given time interval will be completely delivered from stock on hand. Said another way, a lack of stock will not delay the deliveries. The beta service level is a quantity-oriented service level with back ordering consideration. And then we have also indicator about the expected lead time service level. It's the ratio of orders delivered within the expected lead time at the customer to total orders. Now let's see the bell curve figure. For example, in this bell curve figure, 0.05 probability of stock out corresponds to a 95% service level. In a situation of demand uncertainty, safety inventory is introduced. It can be observed from the figure that reorder point is enlarged by the safety stock subject to a 95% of service level. In order to calculate the service level, then we have the following equation, that safety stock equal to Z times the standard deviation. Okay? So, now we have another area here. This area. Okay, now we have this bell curve. We have two color, white color and the dark color. For white color, it is some kind of area that we provide safety stock to absorb the demand uncertainty at 95% customer service level. And what about this area? It is the area where the risk of a stock out can occur. And therefore, if we would like to minimize the risk, and then we have to shift this line, move toward the right side, meaning that we increased the service level not to 95, maybe to 99%, and therefore we can minimize risk of a stock out. However, if we try to increase the service level, then we have to have a consequence of having higher amount of safety stock, which is formulated according to the following equation. Z times it is sigma LT DLT, that is standard deviation of demand during lead time, and Z is the number of standard deviations. So how to calculate Z? And then we have the following table. Alright, let's say we have a 95% service level and 5% risk of stock out, and then we start from here. We know that the risk of stock out is at 5%, and we start from the cell at the uppermost row, and then we move downward until we found a value that nearest to 95%, and therefore this number, and then we go to the left, to the leftmost column, and we found this at 1.6. So this is the Z value. Alright? Okay, next. Reorder point can be calculated according to different setting of lead times and demands. If the demand is normally distributed at fixed lead times, that the first equation can be applied. Otherwise, if daily distribution of demand is given in a case of demand as a variable and the lead times if is fixed, then the second formulation can be used. If the daily demand is constant but the lead time is variable, then the third formula can be used. Finally, in a case that both demand and lead times are variable, then the last formula is used. Now let's go to an example of using the first formula. Here, average demand for toast process is 35 units per day. Standard deviation of normally distributed demand during lead time is 10 toast process per day. Lead time is 3 days. Service level is 95%. We have to calculate the reorder point and safety stock. So we have information here about the daily demand at 35 unit. 35 unit per day daily demand. This to this. And the lead time is 3 days. 3 days, right? Here. Service level is 95%. We can use Z equal to 165 by using the previous table. Here. Yeah. So the service level is 95%. We have to calculate the reorder point, and therefore we can use the following formula. DLZ times standard deviation of demand. And then we have here D equal to 35 and D35, the lead time is 3, surface level 95%, Z equal to 1.65, and we have also the standard deviations of demand at 10 toast process, 10 toast process per day. And finally we have 122 units. That is a reorder point, a point where we have to make order to our customers, to our supplier. What about safety stock? Safety stock just simply Z times the standard deviation of normally distributed demand during lead time. So 165 times 10 equal to 16.5 units. Now we go to the next formulation, second formula, that is daily distribution of demand is given, meaning that demand is a variable and lead time is constant. Again, the average demand for toast process is 35 units per day, and daily standard deviation of normally distributed demand is 10 toast process per day. Lead time is 3 days. Service level is 95%, and we have to calculate the real point and safety stock. Okay. Here we have reorder point, calculate a formula, and then we just put all number we know from this example. Demand is 35, and the lead time is 3 days, and the daily standard deviation of normally distributed demand is 10 toast plus, and the customer service level 95% gives Z equal to 165, and therefore we have 134 units. And what about the safety stock? Just simply put this. So we have 165 times 10 times square root of lead time is 3 days. So 16.5 times square root of 3. Okay. What about the next formula, the third formula? Daily demand is constant and lead time is variable. And then we have different formula, that demand times lead times times the service level times again daily demand times lead time standard deviation. We have here new variables, that is standard deviation of lead time is 3 days, right? Then we have 25 coming from demand, and then the lead time is 3 days, and then the again times the surface level, Z is 165 times demand, and yeah, it should be times 3, because the standard deviation of lead times is 3 days, right? So yeah, I think we should recalculate this real point. All right. Now the last example. Both demand and lead time are variable. More complex formula, but it is still can be calculated by using calculator or using Microsoft Excel. All right. Average daily demand for toothbrushes is 35 units. It is D, small d. And then standard deviation of lead time is 3 days. Standard deviation of lead time is 3 days. Okay. And then daily demand is normally distributed with a standard deviation of 10 days. Alright. So it is 10 days here. And surface level 95%, meaning that the Z value is equal to 165. And the lead time itself is 3 days. Okay. Lead time is 3 days. Again, the number here is 1, but it's supposed to be 3. Right? 3 square. And then we have maybe different number, but maybe not 170. But that's how to calculate the reorder point with safety stock, where when both demand and lead times are variables. Okay, thank you for your attention during the session 1 week number 10, and see you at session 2 week number 10.